Hello and welcome to the instructional series for the Logic Design class brought to you by HKN, which stands for Eta Kappa Nu and IEEE Honor Society here on campus. To learn more about HKN, come by the eCell at BSE 1.501. So today we're going to be learning about the QM method to find the minimum expression for a group of min-terms and don't cares. So we're going to start out by writing what this expression is. It'll be a four-variable function, f of a, b, c, and d, which is going to be equal to our min-terms of 2, 3, 7, 9, 11, and 13. And we're also going to add in our don't cares of 1, 10, and 15. Now it's important that we leave the don't cares in, as those help us to reduce our final expression even further. If we forget to put them in, we could wind up with a larger expression. So now that we've defined what we're going to be trying to minimize that we would get from plotting out a truth table, now we can move on to solving using the QM method. So the first thing we're going to do is we're going to sort all of these numbers by their binary representation, specifically by the number of ones that they have in every single term. So if we start doing that, we notice that we have two numbers in here that only have one 1. That will be the numbers 1 and 2, whose 4-bit binary representations are 0, 0, 0, 1, and 0, 0, 1, 0. Now we look at numbers that have two 1s in them. In this case, it will be the numbers 3, 9, and 10, whose representations will be 0, 0, 1, 1, 1, 0, 0, 1, and 1, 0, 1, 0. Now we look for numbers that have three 1s in them. In this case, looking at our min-terms and don't cares, it will be 7, 11, and 13, with binary representations of 0, 1, 1, 1. For 11, it will be 1, 0, 1, 1. And for 13, 1, 1, 0, 1. Now, as you may have already guessed, we have the number 15, and there will only be one term with four 1s in the expression, 15 itself, with binary representation 1, 1, 1, 1. And if you're unsure about any of this, you can go ahead and check back where we have 8 plus 4 plus 2 plus 1. 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. Now the next thing we're going to do is separate these into their respective groups. So we separate them into groups of 1, groups of 3 1s, groups of 2 1s, groups of 3 1s, and then groups of 4 1s. Now after we've done this, we start to compare terms between groups. So the first thing we're going to do is compare the groups with 1 1 and the groups with 2 1s. And we try to find individual pairings where there's only one bit of difference between the two. So in this case, it looks like we have 4 matches. The term 1, 3, as the only bit changing is the bit in the second position from 0 to 1. And here, we'll replace that changing bit with a dash. So our term 1, 3 will now be 0, 0, dash 1. Next, we'll have 1 and 9. where we only have one bit changing, the first bit, so it will be dash 0, 0, 1. We next have 2 and 3. Which will have 0, 0, 1 dash, and then we'll have 2 and 10. Whose representation will be dash 0, 1, 0. Nextly, we look at the columns or the terms that have 2 ones in them and compare them to the terms that have 3 ones in them. And we follow the same process. We'll speed this up. So we will have 3 and 7 with representation 0, 1, 1. We'll have 3 and 11 with representation dash 0, 1, 1. We'll have 9 and 11, which will have the representation 1, 0, 1. We'll have 9 and 13, which will have the representation 1, 0, 1. And then finally, we'll have 10 and 11, which will be 1, 0, 1 dash. So finally, we're going to look at, between the terms that have 3 ones in them and the only term that has 4 ones. And here, we'll include all of them because all of them have a single bit of difference. So we'll have the term 7, 15, which will give us dash 1, 1, 1. We'll have the term 11, 15, which will be 1, 1, 1. And then we'll have the term 13, 15, which will have the term 1, 1, 1. Now, if we look through this table, we've included every single term from this side. Now, in some cases, you may not be able to pair some of these numbers with ones in the next column, or you may not have a next column where there's only a single bit of difference, or a next set of rows with a single bit of difference. In that case, those terms would have to move to the very far end, and you would put them in your final chart. Okay, so now we continue this process until we can't reduce the numbers any further. But in this case, it looks like we can combine these terms even more. So if we look between these two sets of rows, we see that we have a couple more matches that we can do. So 1, 3, 9, and 11 still have one bit of difference between them now that we've added that dash. So we can write that down as 1, 3, 9, 11, where the term now is dash 0, dash 1. And we also have the term 2, 3, 10, 11, where we have the term dash 0, 1, dash. So we've used 1, 3, we've used 2, 3, we've used 9, 11, and we've used 10, 11. So moving down, we can go to the next set, and we see that we have more matches of 3, 7, and 11, 15, where we get dash, dash, 1, 1, and 9, 11, 13, 15. The remaining terms are covered by rearranging the terms that we have copied down, which will give us 1 dash dash 1. Okay. So now that we've gotten to this final stage where we can no longer make any more pairs, now we can solve by making our chart. So rewriting our final terms, we had the terms 1, 3, 9, 11, 2, 3, 10, 11, 3, 7, 11, 15, and 9, 11, 13, 15. And we'll write down the representations. Now it's important to remember that these all came from our original set of min terms. So these numbers still represent A, B, C, and D. And so wherever we have these A, B, C, and D, whenever we have a dash, we're no longer going to include that in the final equation. So if we're including, say, this term, it would be B prime and D, where we don't include A and C because they're dashed off. So let's go ahead and solve it using the chart. In this case, along the top of the chart, we're not going to include the don't cares because we only care about the min terms. The don't cares just help us simplify and get to this stage. Like as you can see, we have a couple terms such as the one with 10, the one with 1, and the ones with 15. So those don't cares allowed us to go further in the table and reduce even more. So across the top of the chart, we will write the numbers 2, 3, 7, 9, 11, and 13. Now across this side, the rows of the chart, we're going to fill it in with our final reduced terms. In this case, it was the 1, 3, 9, 11, the 2, 3, 10, 11, the 3, 7, 11, 15, and the 9, 11, 13, 15. And then we mark with X's all of the min terms that we find within these expressions. So in this case, we'll mark down where 1, 3, 9, and 11 are, as long as they're in those min terms. So we'll mark down an X at 3, an X at 9, and an X at 11. In the next set, we'll do 2, 3, 10, and 11. So 2, 3, 10's a don't care, we don't include it, and 11. Next, we look at 3, 7, 11, 15, where we have 3, 7, 11, where 15's a don't care, and 9, 11, 13, 15, where we have 9, 11, and 13. So the next step is to look at where we have prime implicants, or entire columns where we only have one X. In this case, we can see a prime implicant right here. This is not covered by any other terms in that row. So we know that we're going to have to draw a line through that prime implicant. Now with that line, we already know that we've covered the minterm 11, and the minterm 9. So next we look for our next prime implicant, which we also see at a 7. 7 is not covered by any other row with an x and 7. So we draw a line going across, and there we have it. And those are our prime implicants. Here's one more at 2. And we can draw this across. Now, wherever we've drawn across and connected, the vertical lines are already covered. So we've covered all of these terms. We've covered this term up here at 9. And we covered these two terms here at 11. So now we can just transfer over the values of these logical expressions, which have horizontal lines, into our final solution. In this case, our solution for f of a, b, c, and d will look back up at our values for 2, 3, 10, 11, 3, 7, 11, 15, and 9, 11, 13, 15. So we'll look at 2, 3, 10, 11, where we get the value b prime c. This will be ORed with 3, 7, 11, 15's term, which in this case is just cd, which will be ORed with the final term 9, 11, 13, 15, which is AD. And there we have it. This will be our final reduced expression using the QM method.